It can be on. Yeah, it's already on. You can put it anyway. Okay.
All right. Very good. We have working mics. Do you mind if I borrow it for a moment?
Yeah, you're good to go.
All right, we're going to get started. Hello and welcome everyone to session 3. All right, take a moment to settle in. My name is Jaime Fernandez Isaac, and I am an assistant professor in the Electrical and Computer Engineering Department at Princeton University. And I will be chairing this session. And as the co-chair, as a respondent co-chair, we're lucky to have Christoforos Mavrogiannis, who is a postdoc at the University of Washington. And I believe he'll be starting as an assistant professor in the new robotics department at U Michigan. So it's great to have you here. And yeah, we're going to have 3 talks in the session as we have in the previous ones. And it's the same drill as before. The talks will be 14 minutes. I'll do my best to keep the speakers honest. Then we'll have a quick minute for transitions. And then at the very end, we'll have the last 15 minutes of the hour for a Q&A. All right, so great. Without any further ado, I'll pass it on to the 2 speakers who I believe we have for the first paper, Hai Nguyen and Zihan Yang. Whenever you guys are ready.
So, sorry. Hi everyone. So today we are very glad to introduce our paper titled Hierarchical Reinforcement Learning under Mixed Observability. This is joint work between researchers from Northeastern University, Carleton College, and the National University of Singapore. So our work is motivated by one observation, is that there exists some particular problem with partial observability. And solving this problem is equally sequentially solving goal-based subproblems with full observability. And we only have to deal with partial observability when selecting goals. So in the slide, there a simple example. So in this domain, the agent, which is a mobile robot, and it has to reach to the unknown destination C. And because the agent doesn't know the location of C, so the problem is partially observable. And we assume that in this problem, the agent can localize fairly well in the 2D space. And in order to help the agent, there will be an important hint about the coordinate of C when the agent navigates to B. So in this problem, if we assume that we have some navigation policy, which I call go to G here, where G is some 2D coordinate, then we can just solving this domain by feeding the goals sequentially for the navigation policy to execute. So for instance, we can feed it to A and the agent goes there and it doesn't see anything. Then we feed it to B, then it goes there and it sees the hint when and the agent now can go to C. So because we assume that the agent can localize fairly well in the 2D space, so learning the go to Z navigation policy is actually solving a problem with full observability. And compute goals, we need memories here because we don't want the agent to kind of revisit a location that has been explored in the past, or we want to memorize the hints when the agent reaches B. So the way that we're solving this domain is actually similar to how humans perform some manipulation tasks, where the brain is the only component with memory, and it's gonna compute the design process for our legs and hands in order to achieve some design process. And the limbs do not have any kind of memory at all. So we use a framework called motion-based mixed observability (MVP) or MOBMP to kind of describe those particular problems. So in this framework, a state we have two components, X and Y, and X is fully observable, while Y is partially observable. Because X is fully observable, so it's also a component of the observation where we have X and Z. Z is another component of the observation. And we put three assumptions here for a MOBMP. And the most important one is the first one. It essentially says that the dynamics of the environment will be factorizable. And the first component of the first factors will actually be the dynamics of a fully observable underneath. And the other two assumptions essentially it say that the observation and the root function only depend on the next state. So going back to the earlier example, in this example, we can see that the fully observable component, that is the 2D cell position. And the other component of the observation is Z, and this in this domain, that is the hint, which is only visible at B. And the component that is partially observable, that is the coordinate of the destination, which is unknown. And that one is a MOBMP by definition. But if we make the 2D cell position become partially observable, then that is not a MOBMP, because you can imagine that if we give the cell the desired 2D position to the navigation policy, then the agent, there's no way that we can tell that the agent has reached that position or not, because the cell position is partially observable. And the assumption that the 2D cell position, at least at some point, going to become fully observable, actually a realistic one, because if otherwise, then the problem would be too difficult. So we introduced in this paper a method to solve MOBMP efficiently, which we call HILMO. And HILMO essentially, it is a agent with two levels. So the top level policies is a memory-based policy, and it takes in a high-level observation outputted from a summarizers, and then output a goal for the bottom level policy to achieve within K times step. And when the bottom level policies is trying to achieve the goal, the top level policy will stop acting. It will just rest until the next time step. And to create the high level observation, we investigated three ways in this paper. From the K observation emitted when the bottom level policy is acting, we can concatenating every observation here, to get a high level observation. Or we can just take the final observation in the sequence to create the high level observation, or we can put a recurrent layer, to summarize those observations into some fixed length vector. And between the top level policies, it is worth mentioning about non-stationarity in hierarchical learning. The problems arise when we try to learn policies when we try to learn two policies in parallel. So the problem arises because the same state action at the top level actually can lead to different outcomes, because the bottom level policy is changing. It can be exploring, or it is not converged yet. So the same state action can lead to different outcomes, and it kind of create applying the Bellman equation become non-stationary. And to kind of address this issue in our work, we use existing technique called high-side action transition. In this technique, whatever goals is unachieved by the bottom level policy denoted by G unmet here, will be replaced by the goal achieved by the bottom level policy, and then we recompute the reward accordingly with the new goal. We also want to penalize the goals produced by the top level policy if that was not achieved by the bottom level policy, and we use subgoal testing decision where we replace the reward with some kind of penalty, heuristic one. And using this technique, we actually transform an episode, which is non-stationary, where goals were not always met by the bottom level policy, and we transform into some modified episode where goals are always met by the bottom level policy. And we use a policy gradient algorithm called RDPG to train the top level policy.
So now we'll look at the memoryless bottom level policy. So its mission is to achieve any goal G given by the top level policy within K time steps. And so that's actually a pretty generic Go-based Markov decision process that we can solve using a standard deep reinforcement learning algorithm such as the DDPG. And to counter the sparse reward in that problem, we also use hindsight experience replay to deal with that. So for experimentation, we created the following 4 domains. They have continuous state observation and action spaces because that's usually the case in robotics applications. They have sparse rewards, can have long horizon, and they all require some form of active information gathering and memorization. So for time constraint, I'm only going to talk about the middle 2, which are the end, heaven, hell, and the end tag domains. So in the end, heaven, hell, as you can see, there's a sort of a T-shaped maze where you have a 8 degree of freedom and robot in the at the bottom. So the ant robot is rewarded, the agent is rewarded when the ant robot